What was redox short for? Very nice. It's almost like you just practiced that. Reduction, what happens to charge? Charge goes down. Oxidation, charge goes up. The reason y'all are saying that, because I heard people say oil rig. Oil rig is oxidation is losing, reduction is gaining, but it's electrons, it's not charge. So we'll talk about electrons more in electrochem. So right now the easiest and quickest way to think about it is reduction, charge is reduced. Charge goes down. Reduction, reduction in charge. Oxidation, charge goes up. Or oxidation state. Increase in charge. So the first thing we're going to have to do is be able to identify the oxidation state of different elements. Free elements have no oxidation state, so they have a 0. Ions that are charged, their charge is their oxidation state. If you have covalent compounds or polyatomics, you're going to have to utilize clues of maybe knowing one of the oxidation states that are common to figure out the other. So let's just go through this. Copper, solid, what's its oxidation state? 0, because it's a free element. Hydrogen plus 1s? The charge. It's its charge, right? Now, nitrate overall is -1, so we have to figure out the individual oxidation states. We only know one that's the same for sure, and that's the oxygen. If each oxygen is -2, what charge does nitrogen have to be, or oxidation state, for the overall to be a -1? +5, okay? Some of our oxidation states have to come out to the sum of the overall charge. All right, nitrogen monoxide. Nitrogen is going to be, because oxygen is -2, nitrogen is +2. And then we have water. That's an easy one, -2 and +1. And what's copper's here? +2, because it's the charge on the ion. So we can see two things changing charge. Copper is going up in charge. So what does that mean? Copper is oxidized. Copper is oxidized. And then what does that mean is reduced? Nitrogen, correct. Elements are reduced, not compounds. Now the good news is, for some of you, I don't know if you remember those agents, the AP has thrown that off of the exam. You do not need to know the terminology of the agent. All the agent is, for instance, the oxidizing agent is the thing that causes oxidation in the other thing. So meaning it itself is reduced. So it's kind of opposite. But they're not going to test you on it. You don't need to know the terminology. So we're going to get rid of that. Okay, so let's take a look at this. What I want to start with is introducing you to this little character right here that has an OH in it. It's a covalent compound. What class of compounds is that under? Covalent. Families. Okay, she said hydroxide, and it's two different things. No, I'm glad you said hydroxide. Why isn't this considered to be a hydroxide? All before this, what were all our OH minuses attached to? Metals, like group 1 metals, group 2, and so on. So those are your bases, sodium hydroxide, ferric hydroxide, all that kind of stuff. When you have an OH in a covalent compound like this, in some crazy organic compound, this is a functional group that makes this whole thing an alcohol. So get used to seeing alcohol, because this is going to have some attributes that are really important in molecular forces later on. And I'm going to be using alcohols, for example, a lot. Using alcohol for example only. Just saying. Okay, so let's go ahead. This one's seems a little tricky, but it's really not, because our O's and our H's are always going to be standard charge, unless it's like a weird hydroxide or a hydride, something crazy. So looking at this, we know that this is a +1. This oxygen's a -2. These are +1. That's 5 of them. So far, what is my charge up to this point? 5 minus 2 is 3, +1 is 4, right? So for this whole thing to be 0, both of those carbons together need to be a -4, but there's 2 of them, so each one is a -2. What is O2 here? 0. You're the first group that caught that. Last couple groups, everyone was like, -2. No, it's a free element. Okay, that's how it exists in nature. This is -2, making this carbon a +4. This is -2, making, well, we always know that. All right. So what oxidized? What went up in charge? Carbon is oxidized. It went from a -2 to a +4, so this is oxidized. What is reduced? Yeah, oxygen went from a 0 to a -2, so oxygen is reduced. Got it? Now the fun stuff. Balancing the redox equations in acidic and basic solutions. I'm sure you all remember this. It's not too bad, it's not too scary, but ultimately you are taking two half reactions, balancing them individually, and then adding them up for an overall balance. All you need to first start out with is identify what two things are changing charge. What's one thing? Sulfur, and what's the other thing? Nitrogen. So we're going to do two half reactions. Which do you want to do first, the sulfur or the nitrogen half reaction? Sulfur. So I'm going to take sulfur, and anything that has sulfur in it, I'm going to pull it down. Okay? Now there's a series of steps I'm going to write on the side over here that you can jot down if you wish. I want you to realize this says acidic. I'm going to address that at the end of the problem. So step one is always balance everything but H's and O's. So looking at this, we need to fix that. We need to balance everything but H's and O's. What do we need to do? Put an 8 in front of the sulfur. Good. Now the next step in this process, step 2, is to balance our O's using, who remembers? Water, correct. Is Ryan not here today? Dang it. He hasn't had this before. 3, balance H's with, who remembers? Nope. H pluses. Okay. The next thing then is to balance charge with electrons. You can only add electrons once to one side in order to get the charges on both sides the same. And then at the end, you have to do what I call clean house, cancel things that are the same on both sides, and add them up. So we kind of did the first step already. We balanced everything but H's and O's. Done. Balance O's. That's kind of done because there are no O's. Balance H's. That's done. So now we balance charge. What's the overall charge on the left side? -16. So I can add electrons once to one side to make those two the same. What am I going to do? 16 on the right. What's up? There are no, we're only looking at this half reaction right now. Don't look up at this. We're only looking at this half reaction. So we're going to go ahead to make this balance out, add 16 electrons to this side. So now we're going to take out the other thing that's changing, and you guys said that was the nitrogen. So everything containing a nitrogen is going to come down now. So we're going to balance everything but H's and O's. Done. Balance O's using water. How many? What side? 1 on the right. Correct. Balance H using H pluses. How many? What side? 2 on the left. And they have to be H positives. Why we are allowed to do this is because in water, we're having an unlimited of water molecules in equilibrium with their ions at our disposal. So H pluses, OH minuses, and waters we got, all hanging out. So at this point, everything's balanced except charge. What's our overall charge on the left? +1. And on the right? 0. So where do I have to add to get them the same? 1 on the left. Here is the kicker. If you're doing your job right, you're going to add them to opposite sides of those equations. Because one is oxidation and one is reduction. Oxidation is losing electrons, so the top equation is an oxidation equation. Reduction is gaining electrons. That's the bottom equation. Okay, you don't need to identify any of that, though, to do the process. So we're going to go ahead and add these up. But I have to add and lose, gain and lose the same amount of electrons in both half reactions, so I've got an issue. What do I need to do to fix that? Exactly. I need to multiply the bottom equation by 16 because I have to have a common factor of electrons. So I get 16 here, 32, 16, 16, and 16. So before I add these up, I like to go ahead and cancel things out on that are on the left of the arrow and on the right of the arrow with each other. What should always cancel immediately? Electrons. If your electrons don't cancel, you're in trouble. And in this case, we are pretty much done because there are no waters or H pluses on both sides that we have to clean up, so we can just write our final answer. I don't care what order you write it in, whether you start with the bottom or the top. I don't even have my own pattern. And that is our balanced half reaction. Full reaction, using the half reaction method. Now, remember this whole acidic thing? What does it mean to be an acidified solution? Well, there should be not hydrogens. Let's be more specific. Okay, what is that? What does a proton translate to on the table? Hydrogen ions, okay? So looking at this, do you see how we have free-floating H pluses? That means we're an acidified solution, so we're done. Okay, now don't write this down. I just want you to watch. What if this said basic up here? What would you do? You would do everything exactly the same to this point. Then you're going to do what, Will? You're not completely wrong. You're going to add enough hydroxides to both sides. Not to balance out, but we want to do two things. We want to tie up these H pluses, and we want OHs floating around by themselves. So by adding 32 OH minuses to each side of the equation, don't write this down because this is not a basic problem. I'm just kind of faking it. That ties all these H pluses up and makes 32 what? Waters. So we have 32 waters here, and now it's basic, not because this is gone, but because we have that many OH minuses floating around. Okay? So what we'd have to do at this point, if we were going to make 32 waters here, I would have to clean house a little bit and get rid of some waters. I can't have water on both sides of the equation. So I'm going to get rid of as many waters I can from any one side to get rid of it totally. So if I get rid of those 16, how many would leave over here? 16. So I would have no water on the right and 16 over here. So that's how you handle the basic. This is not a basic problem. We'll do the next one as a basic. I just wanted to kind of show you how to do it ahead. So let's move on to this one. This is now permanganate plus an iodide makes MnO2 plus iodate. What do you want to do first? What two things are changing charge? Manganese and iodide. So iodine. So which one do you want to do first? Manganese. All right. So MnO4 minus goes to MnO2. Here we go. Balance everything but H's and O's. Done. Balance O's using waters. How many what side? 2 on the right. Balance H using H pluses. How many what side? 4 on the left. All right, now we're going to balance charge. What's my overall charge on the left? +3, and my overall charge on the right? 0, so I'm going to add 3 electrons to the left. So that's one half reaction done. Now let's take a look at the other. Anything that has I in it, I'm going to pull out. Balance everything but H's and O's. Done. Balance O's using water. How many? What side? Balance H using H pluses. How many? What side? H pluses. Okay, be careful here. What's our overall on the left? -1. What's our overall on the right? +5. So I need to add them to make them equal. How many electrons on the right? 4. I heard 5. I heard 4. Neither of those are right. How about 6? That gets rid of this and this, right? So we have a negative and negative. Oh, math is hard. I know. You guys can do very complex things, but you can't add. Huh? It's just Dwight? I don't know. I heard more than Dwight giving me wrong answers. Okay, so before we can add these up, we need to multiply what by what? The top by 2 to get us the same number of electrons, right? So this gives us here a 6, 8, 2, 2, and 4. So let's go ahead and cancel what we can, clean some stuff up before we write all the mess. What goes? Electrons have to go. And we're utilizing this as the sides, right? Left and right. What's the same on both sides? We got water on both sides, and I can't have that. I got to clean the house. So how many am I going to get rid of? 3. If I get rid of 3, I'm going to get rid of all these, leaving me with how many here? 1. Okay. What else do I have on both sides? H pluses, I have 8 and 6. If I get rid of all 6, that leaves me 2. Did you notice how after cleaning house, the H plus is on an opposite side to the water? That's not a coincidence. That's another internal check that you can use to make sure you're doing it right. Okay, so our final answer, we have 2 H pluses plus 2 MnO4 minuses. My question to you, is this really our final answer? What's wrong with it? It's basic. It's a basic problem. I'm glad you get it. Okay, so we have to make this basic. Currently, it's acidic because of these OHs. So what do I want to do? Add 2 OHs to both sides. The reason I'm putting in parentheses, because when I don't, it looks like it's 20 H minuses, which just bothers me. So that's going to tie these 2 up and make what? 2 waters. Okay. But now, what do we have to do? We've got to cancel the waters and clean house. We're going to get rid of this water, leaving us behind 1 water. Right? So our final answer, H2O plus 2 MnO4 minus plus I minus gives you 2 MnO2s plus IO3 minus plus 2 hydroxides. Bam. Good times, huh? Not hard, just a little puzzle. I know some of the pre-AP teachers gave you like mnemonics, and I forget them. All oranges, wait, let's remember it. All oranges have citrus energy, or all orangutans have. I know these are it because all oranges have citrus energy. So you balance all but H and O. You balance O's using water. H uses H pluses charged with electrons. So there's something about a chimp and an elephant. And angry orangutans hate cheerful elephants. Okay. Angry orangutans hate cheerful elephants. Yeah. That's an alternative method, but my issue with that method is that it's a different method, and I'd rather you guys pick one way, and then you don't change it till the very last step. If you choose to do it that way, it's fine, but you're going to have to remind yourself to, oh, I'm not adding H pluses this time, waters this time, I'm adding OH minuses. I think it's too confusing. I think this last bit is too easy not to do. Okay. Angry old hags. Why are you like apologizing for it? You're insinuating I'm a hag, so you don't want to hurt my feelings? What? I'm really confused.
Everything I said in this class is like turns against me.
The first time was fine, and then oh my gosh. Okay, so this is the grand poobah of all problems. This problem literally encompasses everything we've done this unit so far. Okay? It's not scary. It's actually kind of empowering how much power you have as chemists at this point. How few people in the world could actually solve this problem? Very few. You're in the top 10, not all high school AP kids could do this, I can promise you. Okay, so, no, that's not fair because then I'd have to answer a biology question, and I don't know biology. So looking at this, we are basically, and I'll kind of break it down. There's a reaction here. This is a redox reaction, okay, because we have things changing oxidation states. So that's how you know you have a redox reaction. There's multiple parts to this. They're giving us a solution that we have to prepare. Then they're taking that solution and they're doing a titration with it to find the concentration of something else, which would be the goal is to find the concentration of Fe+2. So ultimately, this first solution we have to make is a stock solution. It's kind of similar to the NaOH in your titration lab. Did you guys know the concentration of that NaOH in the titration lab? Yeah, you had to. So they're giving us everything we need about that potassium dichromate stock in order to figure out its concentration. Once we know its concentration, we can then utilize the titration information. This would be the moles at the equivalence point to find the moles of the chromate, which we could then stoich over to the moles of the iron. But to do stoichiometry, what do we need? What does that equation need to be? Balanced. And it's not. So we have to balance it using half reaction method. So here we go. What do you mean is this going to be on the test? Of course it's going to be on the test. Huh? Hold on, I'm going to cover the mic. It's on the test. All right. So looking at this problem, we need to balance it. What two things are changing oxidation state? Chromium and iron. Why are you talking about being white? And what does that have to do with chemistry, specifically iron? Oh, because he's Asian, and Asians are good at math, is what you're saying. I got it. Okay. I'm a little slow. There is so much racism going on right now in this classroom. I'm really upset. I apologize for you watching this video. This is out of control. There's nothing I can do about it. This is like one of those nightmares where the students take over and I'm standing here not knowing what to do. So we're going to go ahead and deal with one of the two things. The iron to me looks like a good place to start because that's a simple little equation. Iron plus 2 going to iron plus 3 if we want to balance that puppy. Actually, I'm going to move all of this over closer to the left so I can have room to do work on the right. So iron plus 2 going to iron plus 3. What do I need to balance that? Just the charge, right? Everything but H's and O's, O's, H's, it's all done. So we're going to add 1 electron to the right. Now let's look at the other half reaction. It's a bit more menacing. And we're going to have a dichromate, Cr2O7, -2. Hope you can read that. Going to chromium plus 3. So balance everything but H's and O's. We need 2. It's not done in this case, so we need to put a 2 there. This is what most students are going to miss when they're doing this problem. They get so anxious to go and add waters, they forget that first step. Okay. Now balance how many waters are needed. 7 on the right, giving us how many H pluses necessary? 14. So we have an overall of what charge on the left? 12 on the right? 6. So we need to get both sides equal to 6, so that means I'm going to add 6 electrons to the left. So to add these up, I got to multiply this by 6, 6, 6. That's double. I know. Oh, my God. Those cancel. And I really don't need to worry about waters and H pluses. Well, that should be an H plus. Getting rid of those because they're only in one equation. So I've got 14 H pluses plus 6 iron 2s plus a dichromate. Gives us 6 iron plus 3s plus 2 plus 3 chromiums plus 7 waters. All I care about in this problem, though, if I'm being perfectly honest, because we're doing this weird titration and we're looking at the relationship from a known to an unknown, this is what we know and that's what we're looking for. I only care about that relationship. It's a smiley face. So sweet. Okay. So now let's start our problem. We had to get to this point to start the problem, honestly. We needed a 1 here and a 6 here. And now that we know that, we can do some work. We need to find something out about our stock. What do we need to know about that stock before we can put it in the burette? The molarity, correct. So they're taking that much potassium dichromate. So I'm going to start a little stoichiometry over here, a little dimensional analysis. Okay. And I want to get to molarity. I know I have 800 mils, so what do I got to convert the grams to? Moles. And our molar mass is 294.2. So for every 1 mole of this, I have 294.2 grams. So that gives me moles of K2Cr2O7. Now I'm going to do something. Hold on. Fasten your seatbelts. 0.800 liters. Are y'all okay with that? You know what that does? What are my units? Moles over liters. That gives us our molarity. It's okay that you don't have anything up here. It's all right. Look at the units. That's how I passed physics in college, right there. If the units worked out to the answer that they were looking for, I didn't even know what I was doing. I just knew how to flip numbers and make the units work. Seriously. So that's what's going on here. So what do we get for our molarity? It's okay. It's on the board, but I'm all good with that. All right. So that is the concentration of our stock. So now let's revisit what we have and what we're looking for. Whoa. Whoa. It's possessed. All right. So this is our known right here. We know this is 0.0273 moles per liter. We're going to put that in the burette, and we're going to titrate that against, how much of the iron? Was it 250 in the problem? I can't see it anymore. 250 mils. So we have 250 mils in a beaker underneath a burette. We titrate, excuse me, and how many mils did we titrate? It gives it in the problem. No, we already, that's, no. 21.35. Where did the 800 come from? That was to make the stock that was in the bucket under the fume hood that you took to put in your burette. But you actually titrated 21 point what? 35 mils. Okay, so in order for us to figure out molarity here, what are we missing about this iron? We know we're looking for molarity. We know mils. What do we need? We need moles. So we're going to have to do stoichiometry from here to here. So what do we need, though, to cross the mole bridge? No, we already got that. But what do we need before we can cross the mole bridge? Moles. So let's figure out moles of our known. Take 0.0273 times molarity times liters, 0.02135, and we get 5.83 times 10 to the -4 moles. But keep in mind, this is potassium dichromate. How many moles of chromate does it mean that I have then? Oh, 2. What? Whoa. Y'all are freaking me out now. If I have this many moles of potassium dichromate, how many moles of dichromate do I have? 1, right? Okay? Not 1. Hold on. No, the same. I have the same number because for every one of these, there's one of these. So that means that I have 5.83 times 10 to the -4 moles of dichromate. What if it were potassium I was looking for? Correct. I'd have to multiply the moles by 2 because there's 2 potassiums. So we're going to start now our little stoichiometry. 5.83 times 10 to the -4 moles, and we are okay just to write dichromate because that's what's in the balanced equation. And then how do I get from mole bridge? What's on the top? 6 moles of Fe plus 3, and on the bottom, 1 mole of dichromate. All right, that's moles. Do you want to do the little molarity trick? Okay, so what would be the volume then I know my molarity now, moles per liter. Our liter is 0.250. 0.250. And so what is our concentration of Fe plus 2? 0.0140 moles per liter. Do you have questions about that? Because that is, like I said, the grand poobah of all questions. Cough, cough. Yes? It's okay. Hopefully the math is correct from earlier, but it's the molarity of 0.0273 times the liters of 0.02135. Moles times molarity. Got it? Not moles. Mils times molarity. Mils in liter form, of course. Okay? All right, so you've got about 10 minutes to start working on your homework. In German, that would be Hausaufgaben. Everyone say that, Hausaufgaben. Good try.